In this video, we're going to look at some examples of exponential growth and decay in which we need to find the time or the rate. Let's look at this first example. A new car costs $25,000 and decreases by 4% per year. In how many years will the value of the car drop below $10,000? Alright, so let's look at our model here. And I'm going to use these variables. You may use different variables depending on how you learned it, but they mean the same thing. The Q sub 0, that's our initial amount that the car cost. So here we've got $25,000. That's the initial amount that the car cost. And it decreases by 4% per year. So that's our R value. So we're going to put in minus, because it's decreasing, 4%. In how many years? So we're actually trying to figure out T here. Will the value of the car drop below $10,000? So here's our equation. Let's clean it up a little bit. So we got 10,000 equals 25,000, and this is going to be 0.96 to the T. Now, if you're in a algebra-based class, you can solve this with logarithms. I am not going to do logarithms in this video here. I'm going to just show how to do this by guess and check. But if you do need logarithms, then you should look that up. Alright, so what we want to do first, since this 25,000 is multiplied by this, we're going to divide by 25,000. Alright, so 10,000 divided by 25,000. We can put that in our calculator. Actually, all the zeros are going to cancel out there, so we can just do 10 divided by 25, which is 2/5, which is 0.4. Alright, so we have 0.4 equals, don't need those parentheses anymore, 0.96 to the T. Okay, so to guess and check this, all I'm going to do is I'm just going to guess a certain number of years. Let's say I think maybe it's 10 years. So I'm going to go 0.96 to the 10th power. So that's going to drop to 66%. I need to go more years. Alright, so let's try, and maybe we could make a little chart of our results. That's kind of a good idea. So I picked a certain number of T, and then I'm getting my output here. I picked T to be 10 years. This isn't exactly the value of Q. I'll just put output here. And we came out to 0.66. So that'll kind of help us keep track of what we've done. So let's try 15 years. So I'm going to go 0.96 to the 15th power. Alright, that's 0.54, so that's not enough either. 0.54. Let's try 20. 0.96 to the 20th. Ooh, that's pretty close. So that's 0.44. Alright, let's try 22. 0.96 to the 22. That's 0.41. That's going to round to 0.41. So let's try 23. 0.96 to the 23rd power. That's 0.39. So for our uses right here, we can say between 22 and 23 years. Somewhere around 22, 23 years. Now, like I said, you can solve this exactly with logarithms. And if you know logarithms, great. But for this particular course, we're not going to worry about solving this with logarithms. Alright, let's try another one here. A population of bacteria is currently 2.5 million at increasing by 85% per hour. When will the population be over 1 billion? Alright, go ahead and pause the video and see if you can figure out the answer to this question. Alright, well this sets up just like the other one. The numbers are a little bit scarier with the millions and billions and stuff like that, but it sets up the same because we're given the current population of 2.5 million. Now I could write out all those zeros, but I think I'll just do this in millions. I think I'll just do Q and Q sub 0 in millions. And then I don't have to have all those zeros hanging around. And I I have my rate is increasing at 85% per hour. So my t is going to be measured in hours. That's important. And then I want my population to be 1 billion. All right, so I need to put 1 billion in here. So let's write out 1 billion and think about how many millions that is. All right, so there's 1,000, there's 1,000,000, and there's 1 billion. So millions has 6 zeros in it. So 1 billion is 1,000 million. 1,000 million is 1 billion. So here's my equation. So it's a lot like the other one we did. Remember we did, when we did this one, the first thing we did was divide off this initial amount to the other side. So that's exactly what we're going to do here. We're going to divide both sides by 2.5. So 1,000 divided by 2.5, I think that's 400. 1,000 divided by 2.5, 400. So I have 400 equals 1.85 to the t. So we got to kind of figure out, this is almost 2, so it's kind of thinking like 2 to what power is 400. So let's set up a little guess and check table over here. Again, you could use logarithms to solve this, and if you know logarithms, great. Go ahead and use them. Let's try 10. I'm just guessing, right? I'm not doing this with any. That's actually pretty close. It's a little high, right? So if I let my output be 10 years, I'm going to get, was it 469? 470, we could round it. So I need a little less. Let's go 9. So 1.85 to the 9th. Oops, I didn't put, let's try that again. 1.85 to the 9th. That's 253. All right, so we're gonna have to let's try to go to the 10th, right? We see we've got between 9 and 10. We know it's between 9 and 10, and t is measured in hours. So we already know it's between 9 and 10 hours. That's pretty good, but let's get a little bit finer. Let's try 9.5. So 1.85 to the 9.5. That's 345. Okay, so we know it's more than that. Let's try 9.7. 1.85 to the 9.7. That's 390. We're getting pretty close. Let's try to get it to the 10th. 9.8. 1.85 to the 9.8 is 415. Okay, so we know it's between, we know t is between 9.7 and 9.8 hours. And it's hours because this was increasing at 85% per hour. Now let's talk about 9.7 hours. All right, let's clear this. So we know 9 hours, and 0.7 hours, if we wanted to get the minutes, we could multiply that by 60. So 0.7 of an hour is 42 minutes, and 0.8 of an hour is 48 minutes. All right, so we could really narrow this down here and say 9 hours and then somewhere between 42 to 48 minutes. And if we wanted to get a little more technical, we'd have to try 9.75 and keep going, right? But and that's where logarithms really help, is you can get your exact answer. All right, cool. So these are 2 examples of where we have to find the time. In these last 2 examples, we're going to find the rate. In 2020, $12,000 is invested in an account that compounds yearly. What annual percentage rate is required for the investment to double in 7 years? So we're looking at compound interest, and you've done the compound interest formula before. The compound interest formula is really just a version of exponential growth, right? It kind of looks like this, except its amount equals principal times 1 plus the rate divided by the number of compoundings, and then the number of compoundings times t. You see how these are the same? You know, they're pretty much the same. Now I'm doing compounds yearly, so the n value is 1. All right, so if we put 1 in here for n, let's take a look at what this formula looks like now. N is 1, and then if I put 1 in here, I get that. Oops, sorry, I get t. Now this looks exactly like exponential growth formula, where p is my starting value and a is my new value. All right, let's plug in what we know. We know $12,000 is invested, so we'll put 12,000 in there, and it compounds yearly, so we know that's going to just look like this. What annual percentage rate? So we're trying to find the rate, and we want the investment to double in 7 years. So my time is 7 years, and if my investment's going to double, then it's going to be $24,000 is going to be my new amount. Now we're going to be able to solve this one algebraically, okay? So we're going to start doing the same thing. We're going to divide the 12,000. And that's going to give us 2, which really represents our doubling. And now I've got 1 plus r to the 7th. Now, this is kind of the tricky part, and depending on your level of algebraic skill and your comfort level, in order to solve this for r, we need to get rid of this 7, and we cannot distribute this 7 into here. That's not algebraically correct. What we need to do is we need to take both sides to the 1/7 power, or take the 7th root. All right, and depending on your calculator, that's going to maybe determine which one of these that you want to do. So we're either going to take both sides to the 1/7 power. That will get rid of the 7th power. Or you can do the 7th root on both sides. So with a calculator like this, I don't think this calculator does 7th root. But it has an exponent, so I can do it to the 1/7 power. You might Google your own calculator and taking it to the 7th root. So I'm going to write this out. Let's write it this way. Let's see. I'm going to write it like this. So I'm going to take this to the 1/7 power, like that. Now the reason we're taking it to the 1/7 power is because with exponents, when you have a power to a power, you multiply these exponents. And 7 times 1/7 is 1. So on the right-hand side of this equation, I just end up with 1 plus r to the 1st power, which is just 1 plus r. On the left-hand side, now I need to find what is 2 to the 1/7 power. So on this calculator, I'm going to go 2 to the, I'm going to have to put this in parentheses, 1 divided by 7, that's 1/7. So that's 2 to the 1/7 power. And I get this value right here. Actually, on this calculator, I have to hit the equal sign. This, when you close a parenthesis on this calculator, it gives you the value of what's in the parenthesis. So this 0.14 is actually the value of 1 divided by 7. So I have to hit equals, and that gives me 2 to the 1/7 power. Okay, so now I have 1.104. I'll just round it to 1.104. 1.104. So now, to solve for r, all I have to do is subtract 1 from both sides. And that's going to give me 0.104 equals r. And if I write that as a percent, I have 10.4%. So I'm going to have to earn 10.4% per year in order to double my money in 7 years. Let's try one more of these where we have to find the rate. A population follows an exponential model. The population in 2000 was 13,500, and the population in 2020 is 8,300. What is the annual percent decrease? All right, so this is going to be our initial amount right here, this 1350. So we're going to let the year 2000, no, let's try something else here. We're going to let the year 2000 be t equals 0. So this is going to represent times 0. and this is going to be 20 years later. All right, pause the video, set that up, see if you can solve it. Okay, so our initial, well, let's just write I always like to write my equation down and then plug stuff in. So my new population is 8,300. My initial population is 1,350. My rate is what I'm trying to figure out, and the time that passed between these two is 20 years. So to solve this, I'm going to divide both sides by 1,350. Maybe I'll just leave this out and put it in my calculator. Depending on your calculator will determine whether you really want to punch this in all at once. Some calculators are easier to use than others. I could cancel these zeros out. Might as well do that. And now to get rid of this 20, I'm going to take this to the 1/20th power, or you could take the 20th root, because 20 times 1/20 is 1, and so that's just going to leave me 1 plus r to the first power. So now I think I'll punch this stuff in. Okay, so I'm going to go 83 divided by 135. That gives me that number. And then I need to take that to the quantity 1 divided by 20, close the parenthesis, see this value is 1/20th, and then hit equals. And I get 0.976. Now the next thing I'm going to do is subtract this 1 over. So I'm just going to leave this on my calculator. 0.976. Let's do 0.976. I'll just jot that down because we like to show our work. And then I'll subtract 1 from both sides. And I already have this on my calculator, so I'll just do -1 equals. And I get negative 0.024. Negative 0.024. And so if I move the decimal over 2 places, I get negative 2.4%. Now, I would be expecting a negative because the population was decreasing. So the annual percent of decrease is 2.4% per year. All right, well, I hope that helps you guys in figuring out how to solve for time and how to solve for rate.